Okay, good afternoon, morning, evening, everybody. Sorry for the asynchronous lecture, but thank you for accommodating my travel. So today we're going to wrap up some of the conversations we've had around nucleophilic aromatic substitution, electrophilic aromatic substitution, and just a couple of quick reminders. First of all, we have a Canvas quiz this week due on Friday, 5 p.m., as we have in previous. Also, regrade requests are due by this coming Friday, so please get those in for midterm 2. So last class, we talked about electrophilic aromatic substitution, where we really focused on things like synthetic strategies. This is how we put multiple substituents on our system, and then that's how we start to do poly-substituted aromatics. This is where we're using different directing groups and looking at where does the next addition happen, using the rules that we've discussed up until now. And then, like we've just said, most of the time this is an additive effect where one or more groups kind of combine their effort to give you a single kind of an outcome. Now, it's most often we will choose the order of addition so that we get a single compound, but that can be something that actually competes. We'll talk a little bit more about strategies today. Once again, we talked a bit about reactivity considerations. Remember, we can deactivate a group, and if we deactivate something too much, we cannot do things like Friedel-Crafts alkylation and acylation. Those usually have to be done first, whereas more electrophilic systems like sulfonation or nitration works regardless. And final, we talked about protecting group strategies. If we have things like anilines and phenols and we try to alkylate them, then we'll typically get heteroatom like nitrogen or carbon substituting rather than the aromatic ring. So what you're doing is you're taking systems, for example, like an aniline, and under very strongly acidic conditions, protonation becomes the major outcome here, which shuts down the ring and becomes super deactivating. Alternatively, if we had something like a phenol, there's less of a problem with protonation. It's not basic enough to be that issue. However, if we did something like alkylation with a carbocation, then you'll actually get oxygen acting as the nucleophile rather than the carbon. And it's just a preference we've seen with things like phenol as a nucleophile. So in both of these cases where we've got phenol or aniline, which where we have to put an acyl group on. If we convert a phenol into something more like this, now we can use the ring because we've basically capped off the nucleophilicity at this center. So let's carry through a couple of review questions. So take a look at both these two, evaluate them, and think about which synthetic pathway might be better. So I'll give you guys a couple seconds to look at it, think this through, or pause the video and think about what your answer might be. Okay, so if you look at these two, we're doing the same two steps. In the end, we're trying to target this meta-substituted product where we're putting both the acylation and nitration as our two groups that we're putting in, right? Now, think about the two groups, right? So in this case, just in terms of strategy for position, this is a mildly deactivating group, which will be slightly meta-directing. So the position there is still favorable. Once again, nitro is a very deactivating group, which will put this as a meta-director. So there's no issue in terms of selectivity. Both of these two materials will select for meta as being the next compound. So that's not an issue. We're not doing a positional problem here. So we can't differentiate there. If you look at the conditions, all the chemistry is right. There's nothing wrong with these reaction conditions we're applying, so there's nothing special there. The problem comes down to the order. In the first case, we are acylating, which does a mild deactivation, and then we're following up with a very powerful electrophile, in this case our NO2+, to get a meta-selected product. It's already slightly deactivated, and then we do this addition. That's totally fine, no issues. Over here, we're putting a nitro on first, which is a powerful deactivator. We're turning off the relative nucleophilicity, and the resulting acylation is going to get a lot harder. It's going to be very difficult to do it in this thing. So I'd say the right order is this example here, not the second one. And that's just because you're forming a very deactivated group. So today we're going to talk through electrophilic aromatic substitution, talking briefly about what we call blocking groups. This is similar to what we talked about with acylation, just as a way of modifying reactivity in different components. And also nitrogen in the benzylic position, how that sort of impacts points. We'll also talk very briefly about aromatic heterocycles. These are non-benzene aromatic molecules that have a little bit of a different reactivity. Then we're wrapping up all of our acyl substitution with a couple of different pieces, what we call diazotization, so adding a diazo group to it. So it's this fragment here that you want to pay attention to, and then how we use those aryl diazonium materials for other reactions. That bridges over into our final topic, nucleophilic aromatic substitution, what we call SNAR. So notice this notation here. This looks a lot like SN1 or what we've called, before SN2. So they're similar in family to actually almost kind of like an SN2 reaction. It's very specialized because we're using an aromatic group as our electrophile. So first, we're going to talk through how we use potentially a blocking group. Now, a blocking group is something that we can add to a ring, so some type of a functionalization. It can be added to the ring in a specific position, which allows us to add some other fragment and then remove this group to give us our final product. This is one way. If you imagine we have something where, let's say this is an electron donating group, it's going to be both ortho and para-selective. And if I really, really, really want this ortho substitution, well, I have to compete with either losing some of the material at that para position. So if I tried to do this direct substitution with whatever this stuff was, I would end up with both the ortho and para products. So one strategy to potentially guide your reaction, what we do is we first do one reaction where we take advantage of the para selectivity. Now you remember, para is generally favored when it comes to steric attacks. So it's possible to do a reaction where we take advantage where maybe the para position is actually more favored, probably because this group might be bulky or something, and we are reacting at the para position preferentially. Once we have that para substitution, if that's where the reaction is more favored, again because of a steric argument, then we can follow up and we do a reaction of our target. So that's where we take advantage of the remaining ortho substitution, which also means this blocking group here generally will be a meta director. So if you notice, the blocking group relative thing is a meta position compared to my donating group here. This would be an ortho para selectivity. So the combined strategy here is we're using the ortho-para activity to select for the para first. We put our blocking group on, which ideally is a meta director. We then add in, we get our target. Now at this, it's ortho here, but meta there. And then we carry an unblocking, something that clips this group off and returns our proton, giving us our selective one. So to think of it, this is kind of like a shell game. We're going through multiple transformations, which gives us the desired regioselectivity that we're hoping for. Now, typically what we would use as a blocking group very often is a sulfonyl. So there's two reasons for this. The sulfonyl, in general, because of the size of the SO3 cation, it's large enough that we typically get a para selectivity. And more importantly, it can be done reversibly. So this part right here, strong fuming sulfuric acid, remember that gives us our SO3H cation, which then allows us to do our electrophilic aromatic substitution. At this position, we can then follow it up with the reaction of choice. In this case, we want to do the chlorination. We generate our Cl+, which is then going to be, remember, if you look at our two positions, that is a activator. It's going to be ortho-para selective to these positions. Sulfonate, or this sulfonyl sulfonic acid, is going to be a deactivator, and it is going to be specifically meta-directing. So that points to this functionalization as being the preferred geometry. Then to cut it off, all we need to do is use dilute sulfuric acid. So this is H2SO4 and water and some heat. That acidic solution with water and heat allows us to actually clip this by first protonating that group and then undergoing sort of a retro reaction. You don't need to know the mechanism of this one specifically, but it's effectively like a reverse version of this electrophilic aromatic substitution kind of step. But effectively, putting that whole sequence together allows us to blow off our SO2 fragment, like a decarboxylation, or sorry, like a, yeah, it's effectively related to like a decarboxylation kind of step. But in the end, we remove the sulfonic acid and return our proton. So next, we're just briefly going to mention aromatic heterocycles. Now, heterocycles are molecules with a oxygen, nitrogen instead of a carbon in the ring, right? It's one of our heteroatoms that we've been using through. Now, typically, 5-membered heterocycles include molecules like pyrrole, where we have a nitrogen in the ring, furan, where we have an oxygen, and thiophene, where we have a sulfur. Those are the most common ones you're going to run into. Now, these are all considered electron-rich aromatics, and they are very reactive towards substitution. You can kind of imagine that imagine benzene. Benzene has 6 pi electrons over 6 atoms. This is 5 atoms and still 6 electrons. So there's a higher electron density in the ring compared to something like benzene. As a result of that too, they're very commonly better nucleophiles than benzene. So if you actually had both, the furan or the thiophene would react preferentially to benzene in the same molecule. Now, if you look at this and say, well, there's really, because of symmetry down the middle here, I've got that center, I've got 2 of them, this red center, and then I've also got this pink center here. And if I was going to substitute at the red center like this, I get this compound. Substituting at the pink center, I get this one here. Now, looking at these two, which one do you think would be preferred? Well, the answer is actually this red one here. And you can kind of look at it a couple ways. One way might be, oh, hey, look, I've got an oxygen. It's immediately next to this center, so I've got a very electronegative center that I've got an oxygen carbon plus next to it that may be disfavored. It actually comes down to the resonance structures. So over here, the only resonance structure I can really draw to delocalize that charge would be a donation like this, which gives me something I could potentially draw like this, where I have my electrophile and hydrogen over here, and that's really it. I can't actually extend the ring any further this way. Trying to do this kind of thing to satisfy that charge would actually over-hybridize that center, right? I'd have to break a sigma bond, so those are not valid resonance structures to further delocalize in that direction. Up top here, though, on the red one, I can make this kind of resonance structure where that would now look like this. Where I have my hydrogen, and here where I've got my lone pairs. And if possible, you could even say that I can even go one more further, right? Adding to that center over here creates further one where I can draw it like this, hydrogen and my electrophile, positive over here. So effectively, the positive charge in this first example is effectively shared out over this whole part of the ring, where the oxygen plus, what we're sort of invoking over here, this is a pretty minor contributor because it forces a positive charge onto a very electronegative atom. The major ones are still this one's over here, and we've spread it out over 4 centers. In this case here, the resulting positive charge that we form is really only spread out over 2. So the range of the delocalization is limited when we have this structure as compared to that one over here. So this becomes our preferred geometry that we would go through. Now, one thing we want to call attention to is the relative flexibility of this nitrogen on the ring. So specifically, if I have this aniline here, there's a lot that we can do with it. Remember, an aniline on its own is a very strong donor. Granted, it has problems being acid-base, but we can cap it in this way to kind of remain that donor kind of potential, but it's at a different oxidation state compared with something like the nitro group here. This is a very, very strong withdrawing group, And as a result of that, depending on which end of the spectrum, if I'm on the very oxidized side, I've got a meta director that's deactivating. It can shut down the ring for certain points, versus if I reduce it and then block it, I've got an orthopara director or another orthopara director where this one is, activating. And likewise, this is mildly activating over here. It's this composition where I've got all these different sort of points. I can swing it in the nature of how the ring would be functionalized just based on the oxidation state of this nitrogen. So it's actually very beneficial to put a nitrogen on the ring and then manipulate its oxidation state in order to change the electrophilic properties of the ring. So that just means I can sort of do this kind of back and forth, right? I can have a strongly deactivating, strongly activating, or even mildly activating, really just based on what happens to be substituted onto it, what group happens to be present, and what oxidation state here. So it's a very useful thing to have on the ring. There's actually one more thing that we can do, actually, which comes down to the aryl diazoniums. So in addition to what we just said before about, oh, look, I can maybe change the directing capability or the relative reactivity, I can actually go through and do this one more conversion. This is where we take an aniline at this reduced oxidation state, and by reacting it with sodium NO2 or sodium nitrite and HCl, this produces a reagent we called HONO, H-O-N-O. So it's a lower oxidation state than nitric acid. It's actually nitrous acid. You notice it's one oxygen down from the higher oxidation state. And this species allows us to form a very stable, very rare nitrogen to nitrogen triple bond. If you notice that, that's nitrogen gas barely held onto the molecule by way of a carbon. The other diazonium that you run into before is diazomethane. Remember, that's CH2N triple N. Just like that, this is formally positively charged. Negatively charged is how we would sort of draw this, or it has, the other way to draw this would be to have, in this particular case, we'd actually draw this as carbon minus. The other formal one would actually be carbon CH2 double N, where this is now still positively charged and negatively charged over here. These are the two resonance structures that we talked about during esterification. And just like those, what these kind of diazo reagents are, it's effectively a very, very good leaving group, nitrogen gas, that's barely attached to this carbon to make these very energetic molecules. So once again, I've got almost nitrogen gas that's being held on very lightly by a very weak bond. Effectively, what this does, it allows us to convert the relatively stable aniline into an amazing leaving group by adding this nitrogen. We call this reaction a diazotization reaction. So how we do this is we treat it with HONO, and how we get there is the lower oxidation state. So this is our sodium nitrite, right? So we start off with sodium NO2, which gives us this NO2 minus anion. If we treat that with mild protons, we get a proton onto here, and just very much like what we've shown for the other electrophile generations here, adding more protons. So if we protonate a second time, this is where we'd pick up one more proton here. What we've done is we've created a very good leaving group on this side, so we can just fracture that nitrogen to oxygen bond, and that gives us our reactive electrophile. So this is the same theme that we do with sulfonation as well as nitration, right? The higher oxidation components is this under acidic conditions, we're losing water to create our electrophilic reagent. So how the diazotization works is we're using this nitrogen transfer reagent effectively. It's very electrophilic, and as long as we have the right pH, so here the HONO reaction can be done with a mild acid present, so we don't need to go in with quite as strong. We can actually titrate that in or form this one separately. That prevents this nitrogen from being protonated just by making sure we maintain the right pH. So this would be When we put this together, we get a nitrogen attack to that center, and because this is a very polarized and very strong electrophile, we then migrate out the double bond. So we get this species initially. So again, following out, we have our protons over here. And so we've just transferred the positive charge out to that center. If we do our proton transfer, we end up with our neutral molecule. So where we've now formed a single nitrogen to nitrogen bond, and it's still this oxidized nitrogen species over here. Now, if you take a look at this, remember this should remind you of a carbon like this, where we have our alpha protons, and we can tautomerize, right? There's a tautomerization that's possible where we can go from the keto form to its enol form. And similar thing happening here. If we carry out a tautomerization, we redraw this now as, here, let me redraw that, benzene, nitrogen, where we have a double bond, OH, excuse me, that's a nitrogen to nitrogen, OH like this. So what we've done is just move this proton over to this oxygen center. Likewise, we're moving the double bond back here. So it's the same kind of general structure we would have, either protonate on the oxygen and then deprotonate on nitrogen as we move the pi bond, or vice versa. We could deprotonate on nitrogen first and then carry that through. But that gives us this tautomerism where we now have two nitrogen-nitrogen bonds formed. So we're on the way to our final product. The last thing we have to do is eliminate water here. So this is where if we're under still strongly acidic conditions, right, we still have protons available. So you can imagine another proton transfer kind of step where we're just picking off that proton. This gets us to our nitrogen. We have two bonds to nitrogen and now OH2 plus, which means all we have to do is break that bond and fracture something like this to give us this kind of structure here. Actually, no, sorry, I did that wrong. I'm sorry, this should be like an elimination, right? This is our leaving group over here. Lone pair has to come down over here. That forms our nitrogen-nitrogen triple bond. So final product here is nitrogen and then triple bond to nitrogen where it's cationic or overhybridized at this internal position here. So usually these molecules exist as salts. If you follow this part through for charge balance, this molecule here will have some counterion, X minus, for balancing off of our NO electrophile. That counterion would follow the positive charge here. It's then released from the molecule and then again be back over here. So your X minus is whatever your counterion is for your acid, following through as a charge balance for here, and then finally over here where you've just lost one molecule of water. So, excuse me, X minus. Now, typically, this is done with HCl as the acid that's added. So very common, X minus is equal to chloride in these cases. And that's just practically, usually, we're using HCl as our acid, but really it's whatever species, the X minus here really is whatever species was the counterand to the strong acid that we're using. So this is the overall mechanism shown here, again in good copy. Nucleophilic attack to our electrophile that we showed you through the elimination pathway, followed by proton transfer, tautomerization, another protonation, elimination of water to give us our aryl diazonium salt, which again is charge balanced to whatever that X minus species is at the very beginning. Again, most important here, the formation of our HONO is done with mild acid conditions, so just a little bit of HCl, really only enough to do the protonation and dehydration of our HONO step. So it's not acidic enough to completely shut down nucleophilicity the way it is in something like fuming nitric acid or sulfonation. So aryl diazoniums are very, very useful. They're they're great because effectively you can think of this reagent is equivalent to benzene plus, effectively, and nitrogen gas. So there's almost no other way to create this kind of positive charged benzene, where you're literally fracturing this bond over here. You're retaining the aromaticity, but you're breaking this sp2 bond to create that component. So because of that, it is very, very explosive. Like, you can think of this bond here as just barely hanging on. It's a very weak bond just because the products that you can make in terms of the loss of this nitrogen is a very strong driving force. So that's problem one, is you've got the loss of nitrogen here. Snapping this bond is easy. Second is we make this material here that once it is formed, it rapidly reacts to form much more stable products. So you can kind of think of it where the aryl diazonium is sitting right on this precipice. It has a very, so if we think of the energy level diagram, we start off with aniline, we go up to this aryl diazonium, we have a very shallow activation barrier for doing this reaction. That's by way of both the weak bond and also the ability to lose nitrogen, and we go to a much more stable product after this is formed. So that's just shown out here. And by the energy level diagrams that we have, effectively this is almost a carbocation. It's not just a normal carbocation, it is an sp2, it's localized in an sp2 orbital. So that's a vacant orbital sticking out from the ring rather than our normal carbocation, right, which would be a vacant p orbital that has hyperconjugation to help to stabilize it. This is not like that. Just based on how the bond geometry is and how it's set up, it does this formation of a very reactive component. As a result of that, the kinetics of this match what is more similar to an SN1 reaction. What we see is the reaction does not have any concentration dependence on our nucleophile. Effectively, it only runs, or the reaction has rate is equal to K times the concentration of our aryl diazonium species, this guy right here. It doesn't care about how much of that nucleophile you have. So it's really just clocking the formation of this carbocation here. So it's very susceptible to nucleophilic attack. It's an unusually unstable material that you kind of fooled the molecule into forming just based on how we've formed this very stable nitrogen gas. So why it's super useful is you can kind of, once you've made this, it's kind of plug and play. You can almost substitute your aryl diazonium for any nucleophile you want. So if I had, for example, an aryl diazonium and I want an oxygen in there, I can use water, which then adds my oxygen component, plus H plus as your loss. If I wanted to add it by single carbon, add a cyanide, I can add my Cn minus nucleophile to this point. So it's just replacing here. And you can actually even put another nitrogen back in. I can use NO2. In this case, you're using NO2 minus because your counterion here is K plus. This is a nitrogen nucleophile for installing this group here without having to go to your classic nitration conditions. And more importantly too, where this nucleophile goes in always is wherever the diazonium used to be. So it's a surgical way of doing an addition. And because the thing is not resonance stabilized, the carbocation sticking out of the ring, as in the geometry showed over here, like in this position, this carbocation is not delocalized around the ring, which means the position is always constant. It doesn't walk, it doesn't migrate, there's no problems of it going ortho, meta, or para. It only goes wherever this aryl diazonium is. So in that case, you have a good degree of control. Downside is, yes, these are very explosive reagents. You have to be careful with them. On the other side, if I want to install other sorts of groups, I can actually take my diazonium and actually install a fluorine. So here I'm using HbF4 to install F- into the ring. This is a source of where you're actually using effectively fluoride as a nucleophile. If you remember back before, fluorine is a pretty terrible nucleophile. We don't usually put fluorine into the ring. So this is a really good way of effectively adding fluoride to our molecule. There's not another good way of doing this. In fact, usually the Friedel-Crafts kind of way, if I took like fluorine gas, this is actually so powerful that you usually destroy your aromatic. You would actually add too many fluorines, or you actually destroy glass, everything else. A quick piece of UBC history, we used to have a chemist, Sir Barton, who did specialty fluorine chemistry, which requires all manner of very specialized glass. So this is a much safer way of putting a fluorine surgically into a molecule that you're interested in. If you want to install other halides, for example, chlorine or bromine, these are typically done as the copper salts. It just happens that the solubility and reactivity is just perfectly balanced, that an aryl diazonium with, let's say, copper chloride or copper bromide allows me to put either chlorine or bromine into this one. So instead of using, let's say, a sodium salt, they're typically done with these copper salts, where you're using the halide, the X- is your nucleophile. Potassium is very useful in the sense that the potassium iodide is soluble enough to work in these reaction conditions. Adding simply potassium iodide as your source of I- allows you to surgically install iodine into here. Other nucleophiles, if I was to try and install, let's say, a sulfur at that position, so I wanted to add not the sulfate, but I'm trying to add this as effectively my acetate sulfur minus, so a nucleophilic sulfur insertion, I can use these potassium salts of these thioacids. An azide, N3, this is again potassium plus, and now N3 minus, where you're installing this piece here. Now what this ion looks like is actually N, double N, double N, where the minus charge is actually delocalized across the entire piece. These are very useful in a class of reactions known as click chemistry, which allows you to attach biofunctional conjugations onto the ring. And finally over here, you can actually completely delete this and go back to a proton. This is actually done usually with like phosphoric acid, or potentially even like something like methanol, where what you're doing is forming a carbocation and doing what's called proteolysis. You're adding a proton to replace that, liberating nitrogen gas as a result of it. So overall, the main benefits, the diazonium produces a way where we can introduce some very difficult substrates like F-, Cn-, OH-, where there really isn't a good way of creating sort of the electrophile version of these, right? These are all things that are much better as being negatively charged nucleophiles, not electrophiles. They're not strongly electrophilic species. So it allows us to basically reformat a ring, take an aniline, turn it into a diazonium, and then put a nucleophile of choice. And like I said too, it's certain substitution patterns are only possible using this one. It allows us to take wherever there used to be an aniline, an NH2, for example, and then through our diazonium and then nucleophilic substitution, we can specifically put in that X group at that part. So it allows us a good degree of control that actually overrides the normal polysubstitution patterns that you've seen up until now. The downside, it makes retrosynthesis really, really tricky, because it's kind of like the carbonation reactions and like the malonate esters. It's not always obvious to see how you might install that group, because if you're thinking about electrophilic aromatic substitution, where we start off with some type of a substituted benzene, and we're assuming we're going to be adding E+ to put that group in, we now have this other route where you might start from, let's say, your nitro, you carry out your reduction to form your, let me move this, NH2 component, right? If we have that, so I can start with a nitro, I reformat it to a nitro, or to an aniline, and then that aniline is converted over to our diazonium, N2+, which then we bring in our nucleophilic version to give us the final product, where we actually have added our nucleophile onto the ring at that position. So it's more synthetic steps because we have to go through these sort of transformations. It also means that there may be more than one way to potentially make this molecule, where in the case here we're adding it what we think is a nucleophile, but similar molecules, right? Carbon could potentially come in as Friedel-Crafts or as a Grignard, for example, in these 2 points here. So it does make it a little bit trickier for the number of permutations. You do have to kind of get a little bit more ready to see that. All right, so let's work on a couple of ways of applying this. This will help to clarify what I mean about some synthetic strategies for using these kinds of rings. So take a second here. How do you think you might make this? So again, if I was trying directly from benzene, challenge I have from benzene is that if I was to go through and let's say put bromine on here using like a Br plus kind of system, this might be something where I use, let's say, Br2 and FeBr3 as my reagents, right? I'll install the first one, no problem. However, bromine and all halogens they're weak deactivators, but they're also ortho-para directors. So if I was going to try and polybrominate this, hit this again with, let's say, iron and Br3, what I'm going to make is actually probably the ortho or para directed compound, right? I'm actually going to functionalize in the wrong position, not this nicely meta-substituted one. So as a result of that, I can't go through and use the normal activation parameters to build this up. So instead, a better option here might be to, not going to go this route. We're going to start off with bromine, start off with benzene as before. Let's nitrate it first. So I'm going to use my HNO3 sulfuric acid, and we'll put a single nitro group on there first. Now that I've installed that, I can carry out my reduction, H2 and palladium, and that gets me to my aniline. Let me just move that. So I'm going to get my aniline from this one here. Now that I've got my aniline, this is now a donor group, right? Now I'm actually activating this ring for orthopara direction, very strong. And more importantly, it's orthopara directing at these three positions over here. So if I was to, let's say, acylate it first, acyl chloride. Again, the reason I'm doing that is if I'm setting up for a reaction where I'm using something like a Lewis acid or a Bronsted acid, remember your aniline is a group that would potentially bind with one of those and possibly deactivate. Now this is still an orthopara director, so those are the three positions that you are possibly activating. Okay, now that I've got that, and those are the only three positions that are going to be preferential here, I'm going to go through and use a large excess of Br2 and FeBr3. So what I'm doing here is I'm first adding an activator. I'm protecting that activator. That activator is selective for these three positions over here. And then I'm adding a large excess of my brominating reagent because I can activate and hit that multiple times. It's going to put a bromine. Imagine we use 3 equivalents, for example. We just keep going, keep pushing it. I'm going to get 3 of these guys on here where my hope is the aniline and its donor properties will guide each of these possible additions. Again, the goal here is to actually override the native directing effects of your bromine. So as they go in position, this would be sort of the potential geometry that I get. And then if I go through and do cleavage of this, so I hack off the under acidic conditions with water, H3O+, I can now delete that to form my free aniline, right? So this is deprotection. Oh, I'm running out of room. where let's say I have my 3 bromines like this. So now I've got my right sort of relative positioning. I just need to get rid of this. Well, if I was to carry out, first of all, my sodium nitrate, NaNO2, that's my HONO condition using HCl. That forms my aryl diazonium. And then I was to treat that with my acid. This is, remember, we have our the conditions we did before, something like phosphoric acid, H3PO2, or an alcohol like ethanol. So the conditions we talked about right here, this is where I can potentially take my diazo system and replace it with a proton. What I'm doing between those two is I'm replacing this whole group with just a hydrogen, effectively. You just delete it out at that point here. So this is actually how a sequence like this is what people use for making these tri-substituted molecules. This is also a case where the relative directing group of these halogens can be overridden by this aniline effectively too. Again, this is not something that we'd be able to maybe predict a priori. It's something that we measure and we find out that, that this is at least possible. But why, again, this gets difficult is if you're trying to target a molecule and you have a hydrogen where a potential activating group is, it's difficult to see what the strategy might be, so it's difficult to use from a retrosynthetic point of view. Take a look at this one. If we give you that same idea right here where we're saying that we have a very particular substitution pattern we're looking for, and we have the rules we talked about what's allowed and disallowed, think about how you might use the strategies that we've discussed so far in order to make a molecule like this. This would be including things like blocking groups and possibly diazoniums through here. Likewise, take a look at this one. This is another example where you have to be a bit creative about the number of steps that might be necessary and the sort of the distribution that's possible to get through to your target product. I will follow up with those at the end of this video, but give them a try, maybe pause it and go back. So the last thing we're going to discuss is the SN-AR reaction. Again, as a mental primer, remember these are kind of related to things like SN2 or SN1 reactions. Now, up until now, usually what we've done is electrophilic aromatic substitution. This is where the benzene is my nucleophile, and we're tracking some very positive E+. That's everything we've discussed up until now. With these ones, a nucleophile is going to attack the benzene ring. That means that the benzene is actually the electrophile in this partnership here. It's really weird. Only works with some very specific ones, and again, that's you could potentially guess that. Remember, normally benzene is very electron dense. There's a lot of electrons around here, so it's not typically something we see where some negative charge attacks this ring. It has to be done in a very specific way. There's a very specific geometry problem. It's not going to look just like the SN2. It's a little bit different, and again, we need some very special properties of this ring to allow this to happen. In a way, it's more related to something like a Michael addition or something like that. What you're going to do is change the hybridization of a center, and it's very carefully guided where you have molecules like this, usually where there's very strong activating rings on the center. So to make a nucleophilic substitution, like an SN-AR type reaction, what you need is a benzene ring with strong activators. These are strongly deactivating electron withdrawing groups, such as a nitro or more than one nitro point. And what we need to do is use very good nucleophiles, in this case like OMe-. We actually briefly mentioned this as a kind of a weird reaction when we started talking about our ether synthesis. What's happening here is the halogen becomes our leaving group. Fluoride is usually typically used for these reactions, and we're using an alkoxide as our nucleophile, which is substituting that center. So the reaction's happening at this position right here, at the same position that the halogen is attached to. That's where that substitution comes through in this case. So the pattern that we're looking for here is some kind of aryl halide, where that's where it makes up our leaving group. that also has an electron withdrawing group. Very typically it's a nitro, and the nitro is going to be ortho or para, sometimes even both. You may have multiple relative to your leaving group. So you're looking for something where nitro, in this case, is para to the leaving group, or nitro is ortho to my leaving group. And once again, the leaving group here is something like fluoride, chloride, or bromide. In those cases, nucleophile minus is going to attack, and it's going to substitute wherever that leaving group is. That's where the nucleophile gets put on. So it's very specifically linked. Again, a really important thing to see where this happens. It's always where you have a nitro group and a leaving group on your aromatic ring. Nitro is ortho or nitro is para to that point, and the nucleophile is going to substitute wherever that halogen happens to be. So the mechanism of this one actually looks a little bit more familiar than you might think. We start off where the nucleophile is going to attack this ring, and again, it's only possible because you've got very strong electron withdrawing potential. You're pulling this electron density away from this. Now follow the arrows. If I was to do this, and I'm not going to create a Texas carbon, this is where it should remind you a little bit of a Michael addition. If I attack that center, I'm going to have to slide these electrons over. Now again, that's not good. We fixed this problem right here, but we've created a new one over on that center, so it's not going to stop there. We're going to slide them over one more time. So I'm going to push them over. It looks like this. And in this case here, you'll notice, let's draw the Lewis structure over at this center here. So we have our aromatic ring. We have this center here where we have our leaving group attached. The nucleophile is now also attached to that center, and again, it's coming in as a negative charge, so we're transferring the negative charge into the ring. The double bond, there's going to be one that exists down here, and this nitro group, if you notice our arrows right there, are now double bonded here. If you expand that nitro, it's N, O, and O, like this, where both of these will now bear a negative charge. So in fact, if I expand, well, let me just redraw it down here. This molecule, if you actually draw out all the bonds, actually looks like leaving group, nitro, double bond, oxygen here, where we have a positive and a negative charge. So the cascade of your nucleophile attacking that center, that negative charge, is charge hops over, charge hops down. It's possible because of this nitrogen minus, and then we actually continue all the way out onto this oxygen. That's how you get this resonance structure we've shown here. And that's why the ortho and para position is so important. You need this kind of ability to shuttle charge off of the ring in order to allow us to form this new sp3 center over here. Now that's, again, like a Michael addition where we're kind of temporarily pushing charge up onto an acceptor. It's not going to stay like this. It wants to reform its aromaticity. And so to do that, we're going to start bringing the charge back down again. So if we start here, we just kind of walk back through that same sequence. So reforming our nitrogen-oxygen double bond, reforms my carbon-carbon double bond. That's going to push back over here. And so that's just the retro of that very first step that we've done. There's two choices. If I was to just blow out that nitrogen, the nucleophile, we go back over here, it's reversible, and that can happen. The other option was to blow off this group here. We blow off the leaving group. And if that happens, we're going to fracture the leaving group bond. We have our nitro now reformed, still positive over here, and we have our nucleophile now in position here, where we've actually ejected our leaving group minus. So as a result of that, going through this overall sequence, we now have a substitution which looks something kind of like what we've seen with nucleophilic acyl substitutions. So here's what we have as our overall point. This is just the ChemDraw version of this reaction. Wanted to show you again the same kind of pattern exists if we go through with the ortho substitution. It just doesn't have as long of a resonance structure between them. Okay, guys. Wanted to go through these follow-up reactions. So here, if I'm going to try and make this, and it's going to take about more than 4 steps, starting from phenol, how might I do this? So I'm going to start with phenol down here. And this is the sequence I came up with. I think there's other possibilities, so happy to discuss. Right now, the phenol in place, it's a strong donor and orthopara director. But first, before we do any alkylation, we're going to acylate it. That's going to help to cap off the group and protect it from alkylation on oxygen, but keep its sort of activating character. So that's our first step. Next, we're going to put probably, remember this is orthopara directing, so we are activating these 3 centers because acyl is kind of bulky, because we want to put isopropyl groups on there that are also kind of large. There might be a preference for a para substitution at this point. So we want to actually block that first. So we're going to do H2SO4 under strongly acidic conditions. That's going to give me a sulfonation first. So I'm going to put SO3H down here. We've got this group, and that allows us access to these remaining. So remember, sulfation here, this group is going to be meta-directing, while this group is going to be ortho-para directing. But we've blocked off the para position, leaving those 2 ortho positions up for grabs. So now the ring is not totally deactivated. We've got an activator and a deactivator. We can take on something like Friedel-Crafts alkylation, not acylation, because we're attaching a secondary center over here. So we can take something like this, iron trichloride. That's going to get us our substitutions, where we're going to probably push it hard enough, large excess, to get 2 substitutions, 2 isopropyls adding on both sides. We still have our SO3H here. So now we have to carry out a D protection. Now we have the right parts. We need to remove this blocking group. So that would be with something like dilute sulfuric acid, H2SO4, and water. And in fact, under those same conditions, these are like our saponification conditions. Strong enough water, dilute sulfuric acid, and heat will allow us to also hydrolyze this group 2, which should get us our final product, removing that blocking group over here. Okay, for our next one, this takes a number of steps. There's a whole bunch of different geometric manipulation, and we're going to start from toluene. Okay, now first thing we have to do is we're going to nitrate, so HNO3 and sulfuric acid. That'll get us both the ortho and para, but for now, let's say we take this and we're going to do a separation. I'm going to mention this is both ortho-para directing, but we're going to isolate the para substituent by some sort of separation. This is a case where we don't really have a good way of beating that now, but we get mononitration is what we're targeting first. Okay, now that we have that, now that we've installed that nitrogen, we can go through and use its properties as a potential directing agent. So I'm going to go through and actually reduce this. So hydrogen over palladium. That's going to switch me over to my NH2 and my methyl. Great. Next, now that this is an amine, we've got sort of 2 things competing, right? The methyl group here is going to be targeting, methyl group is going to be targeting orthopara like this, whereas the aniline is targeting orthopara like that, where the aniline is a much stronger director at that point. So this is the center we want to sort of functionalize onto, and this as a donor is one way we can potentially access it. So what we're going to do is acylate that first, give us this. That then allows us access to a pretty good donor, still stronger than the methyl. And now we can carry out amide winning the sort of the war. I could now nitrate this again, so that's HNO3, H2SO4, to give me my methyl, N-acyl, and let's say nitro. Again, might not be totally perfect, but at least we've got a stronger donor here to give us, this is kind of the major product here, where the amide is winning the tug of war between those two centers. Now that we have this, our follow-up is to finish basically replacing that nitrogen, this one down here, with the right oxidation state. So if we use water and acid and heat, we can potentially cut that group off. So we have our methyl, we have our nitro, and we have our NH2. Again, it's the wrong oxidation state. If you had the conditions, you might just be able to oxidize this up, or this is where we can go back to our diazo, right? We can't really do a direct oxidation of this one. If we use something like Jones reagent, we'd actually oxidize this center as well too, because it's a benzylic CH2. So the better option here is to go through and use our sodium NO2, HCl, that's our aryl diazonium, and we follow that up with our nucleophilic, that's KNO2. Remember, this is effectively our NO2 minus nucleophile. That should get us to our final product over here. So this is kind of a stepwise sequential 1-2. Now there are some complications. We don't have great selectivity here. We're forcing a push-pull behavior here. But at least as we go through these sequences, this is kind of how we might practice out the manipulations like we've discussed.